Hello, everyone. Just to introduce myself, my name is David Lewis, and I work at EasyPower. And today I am pleased to present the seasonal analysis for grounding systems webinar. So the purpose of this presentation today is to display the effects temperature variation can have on a grounding system's performance and demonstrate the XGSLab's seasonal analysis tool to help evaluate that seasonal variation. At the end of this presentation, it's my goal you'll be able to identify when seasonal temperature variation can significantly affect your grounding system's performance or a system that you're evaluating. I want you to be able to explain how soil temperature affects the soil resistivity. And my goal is that you would be able to use the XGSLab seasonal analysis tool by the end of this presentation. So to get those goals accomplished, we're going to give everyone some background on soil resistivity and discuss the seasonal ground temperature variation that we see and how that relates to the seasonal variation in soil resistivity. And then we'll switch over to the XGSLab software and do a case study to evaluate a grounding system's seasonal performance. First, let's cover the basics of soil resistivity. So primarily we have two types of electrical conduction in the soil. There's the electrolytic or ionic contribution, or we have the electron or electronic contribution. When we are discussing the electrolytic contribution, we're primarily looking at the ions in the soil are the moved charged particles, or the charged particles that are moving, providing that current flow. With metals, it's more similar to what we're understanding with the electronic contribution, where it's really the electrons are the particles that are moving and creating that current. So when we look at a material such as soil or the earth, that conduction or its resistivity is primarily a factor based off the electrolytic conduction. And an example of that at a really basic level is if we have a sodium atom, such as on the bottom of the screen here, it's balanced on this image. But once we drop that sodium atom into water, it really quickly loses its valence electron. And then that atom becomes a positively charged ion. And this is what we're talking about when we're discussing the electrolytic solution or ionic contribution for current flow. Now I wanted to talk about the basics of how we are conducting current through the soil so that we can give some better information or have better estimates for more macro evaluations of soil. Typically, when someone's going out and doing a test or evaluating the resistivity of soil, they're looking at a more macro level, looking at the chemical content of the material, the granularity or particle size of the soil, its moisture content, and its temperature. And understanding what can contribute to greater electronic or greater electrolytic contribution, we can get a better estimate of what's going to reduce our resistivity and what is going to increase our resistivity. For example, if you have a higher chemical content and you have a higher moisture content, you're able to have a more charged ions in that material, so you can have a lower resistivity. Now, when we talk about soil temperature and the effect that has, we really see a dramatic effect when we get to extreme temperatures such as frozen soil. And when the soil is frozen, we actually start to see that those ions movement is not so free, and they really start to get trapped in, and that increases our resistivity dramatically. But before we get into that, let's talk about how resistivity is actually, that information is acquired. Typically, when doing a grounding system analysis, a technician or engineer is sent to the field in which the grounding system will be installed. And the most common method for measuring soil resistivity is using the Winner method. This is an approach where we have a test device which will inject a known current on outer probes that are inserted into the soil, and then we're measuring a voltage on a couple inner probes. And as we expand the distance between these probes, we start to evaluate deeper and deeper soil layers and get an understanding of the electrical characteristics of the soil that we're going to be installing our system. So let's bring in a little bit of how temperature relates to our soil resistivity. So when we are testing material, the temperature of that soil can dramatically affect its resistivity. For example, if you were to measure a sample of clay and that was just above freezing, and then you were to test that same sample when it's 10 degrees colder Celsius, you could see an increase in that material's resistivity of 6 to 10 times just on that 10-degree swing. We have a similar effect when we're looking at a warming effect. It's not as dramatic as we see for the frozen resistivity where we're starting to lock those ions from being able to move. But on the warming characteristic, if we increase the soil's temperature by 20 degrees, we could reduce that soil layer's resistivity by up to half, depending on the material. So what really drives the temperature of that soil is going to be our climate. So when we're performing those measurements that we talked about earlier, it's a measurement, a little bit of a historical measurement. We're measuring the soil resistivity, and as we go deeper, we're starting to measure a little bit of the climatic conditions a week ago, a month ago, or a year ago, based on some of the regional climate of that area and that soil's thermal properties. So we can model or approximate our climate relatively accurately. In North America, there are great records for the seasonal variation of our air temperature. Here, the graph on the left, we have the mean annual air temperature denoted by this dashed line, and we have a fluctuation around that of A, or our amplitude, for how much we swing above or below the mean annual air temperature. And this is approximated just with a sinusoid wave. And we're able to use this predictable pattern in order to calculate what the soil's temperature will be using some of the equations from thermodynamics. So much of the characteristics that we'd look at from a soil sample would be its thermal conductivity, its heat capacity, and its density. And all of that thermal energy information is going to be more succinctly captured when we describe it as the thermal diffusivity. And I expect many of you on this call have a background in electrical engineering like myself. And if you're doing much work in grounding systems, you probably talk a lot more about the complexities that come with geology than you probably would have realized going back to college. So to make things a little simpler, on the left I have a table that shows the typical soil thermal diffusivity based off of some general characteristics or descriptions of that soil. Now what we're able to do is take the mean annual air temperature and translate that into a mean annual ground temperature. And we can use that fluctuation that we saw annually and adjust that based off the depth of the soil and its thermal diffusivity and be able to come up with an approximate or a calculated value for the soil's temperature and be able to use that in calculating its respective soil resistivity at any point of the year. The graph on the right, this blue line tracks pretty well with the previous plot where we had the air temperature displayed. We're the coldest in winter, and we see our peak right in mid-spring, right in midsummer, excuse me. And when we go maybe a meter deeper, we see this green line. We see the amplitude is attenuated for our variation off of our mean annual ground temperature. And we also see a phase shift. And we see this trend continue as we go a little bit deeper into the soil. And I think of this kind of like what you see with large bodies of water, just generally any sort of large mass. It takes some time for that thermal energy to transmit into the soil. So when I'm talking about us measuring some historical information when we go do soil resistivity measurements, this is really what I'm talking about. So how much does it really matter if we do a soil resistivity measurement in the fall, the summer, spring, or winter? Well, if we were to do a measurement in June, but we wanted to understand the soil resistivity and the ground temperature in January, we could say that the soil temperature in the summer is represented by this blue line. We have relatively warm temperature that kind of starts to creep down to the average soil temperature as we go maybe 6 meters deep. Now, in the winter in January, we have really cold soil conditions, and we see this start to creep up and kind of level out at the same point where we begin to match our deeper soil temperatures, maybe 6 to 8 meters. Now in October, we have a little bit different temperature curve. I'm showing the same temperature curve for January, but our October measurements, we're going to see a little bit colder temperature for that Earth's surface. And there's still this little bit of increase, so we haven't fully penetrated deeper into the soil with that thermal energy or the lack thereof when we start to get into the colder months. And if you imagine a scenario, for instance, if I did my measurement in June and I calculated a soil model of approximately 100 ohm meters versus doing that same measurement in October and calculating 100 ohm meters. If you are translating this into a frozen soil model, it's going to make a difference, and that's displayed here. So on the top graph, I have my measurement that I performed in June, and the native soil, or the measurement that is recorded in June, is at 100 ohm meter. And translating the temperature change from June to January and the corresponding soil resistivity increase, I can see an upper soil layer resistivity of approximately 2,500 ohm meters. Now, if I had that same 100 ohm meter measurement in October, that top layer soil resistivity is only, well, it's approximately 400 ohm meters less, which is relatively significant. So understanding when these measurements were performed does provide a difference in how we are evaluating the soil models throughout the year. So let's get on to some case studies. I want to give some background information on the climate of my example substation. So this example, we have a mean annual air temperature of 2 degrees Celsius. This is more northern regions, closer to or in Alaskan region. A 1 degree offset for the ground temperature, and that represents the solar energy that is imparted onto the Earth simply by it sitting there stationary as opposed to the air temperature. And then we have the mean or the annual variation of 14 degrees Celsius. We'll say that our testing was performed in the summer, June 19th, and the soil is characterized as a sandy clay. So here's the XGSLab software, and I have my substation modeled here. And I've already computed the results for that soil model. And in the summer, my grounding system has approximately 0.8 ohm impedance. And with a 5,000 amp fault current, I can see approximately 4,000 volts as my ground potential rise. And what that looks like from a touch and step voltage criteria, we have this plot Green represents locations where my touch and step voltages are below my compliance limits. And the yellow areas represent locations where my touch voltage exceeds my compliance limit. And we don't have any spots on this graph, but red areas would represent where I'm no longer passing for touch or step voltages. Within the outermost loop of our grounding system, we are completely green. So this substation in the summer is compliant for IEEE Standard 80 in regards to its touch and step voltage criteria. But let's go ahead and see what happens when we change this soil model and look at it when it's colder. So we'll go to the Soil tab, go to the Seasonal Analysis tool, and here's the criteria that we talked about in the presentation. The one thing I didn't mention is my date in early spring where my air temperature is relatively close to the mean annual air temperature. This just helps us set that sinusoid wave that we're going to see. So other characteristics, we have our clay and our thermal diffusivity based on approximate value of 0.04. I'll hit calculate here. We can see this familiar graph of the soil temperature as we go deeper. Here we have the blue line representing my temperature of the soil on the measurement day and the temperature of the soil on the day I'd like to calculate my soil model, my new soil model. And my final soil model would increase the resistivity to have the uppermost layer to have 2,600 ohm meter layer, and generally decreasing as we go a little bit deeper into the soil as we decrease in the temperature offset between the measured and the calculated temperature of the soil. So I'll go ahead and apply this. And now my soil model has been changed to my January 1st model. And next thing I'll do is I'm going to update my touch and step voltage criteria. And I'm just going to use a half-second assumed clearing time and apply that. Debug my system, and then I'm going to compute my GPR for this grounding system. Now, as this is running, I changed my touch and step voltage limits because the Earth's surface has a higher resistivity, and that translates to an individual touching a grounded piece of equipment having a higher contact resistance to the Earth. So we see a corresponding higher touch and step compliance limit. So now with my January 1st soil model, I can see my impedance has increased from what we had before, approximately 0.8 ohms to 1.8 ohms. And that looks like a almost 10,000 volt ground potential rise. So I'm going to recalculate my touch and step voltage. And here I'm using a step length of 2 feet, and that represents each of these little red dots. And what those are doing is that's the point where XGSLab is performing a calculation to understand the Earth's surface potential right at this point. And it's going to use that in evaluating the touch voltage criteria from any point on the Earth's surface to each of these conductors. It's a similar concept for the step. However, we're not looking to compare to the grounding system's voltage. Now we're just looking to compare between dots, assuming the person's stride length is 3 feet. We'd be looking in a sphere of 3 feet from one dot to the next. Okay, so that's completed. I will add in my crushed rock surfacing layer, and we'll plot our touch and step safety plot. So we can see a really dramatic difference from our grounding system based off what we had seen in the summer versus what we see now in winter. There are no areas within the substation that are compliant for touch voltages. And in fact, there's just this little area just barely on the outside of the substation that's no longer compliant for step voltage. And this is the dramatic effect that we're talking about that can happen as the soil resistivity increases when you start making a greater contact resistance between the grounding system and the soil that it's touching. There are some approaches to mitigate this seasonal variation, and I think it'd be helpful to go into that a little bit. So let me modify our grounding system, and I'm going to put in some 30-foot ground rods just to make a little bit more of a dramatic effect here. So let me insert some of these. And what I'm anticipating is that in the areas where we have these ground rods inserted, we're going to see better results. It's going to help us maintain contact with the soil that's not dramatically affected by the seasonal variation in temperature, and it's going to help us reduce our overall ground potential rise for that system. Just apply this. And you can see on the XZ axis and the YZ axis, I have now placed several ground rods in the center of my system that extend into deeper soil layers that aren't affected by the seasonal variation in the soil's temperature. Now we'll calculate the ground potential rise and the impedance of our system, and we're maintaining that 5,000 amp injected current. And once this completes, I remembered I have to change the touch and step voltage as well. So first, we have a little bit of a reduction in our ground potential rise. We were at 1.8 ohms for our January 1st soil model. Now, with those additional ground rods, we're able to reduce that resistivity to 1.2, or that resistance to 1.2 ohms, and that reduces our corresponding ground potential rise. And I'm going to change my touch compliance and step compliance limits as well, because we have, oh no, we have the same soil resistivity, never mind. Let's go back to our area calculation. I'm going to calculate, again, the Earth's surface potentials at each one of these points. And as this is doing its analysis, what we expect is in the location where we have these ground rods, we're going to see a better result. We may not see as much improvement to the rest of our system, but just by improving the contact or continuity between the grounding system that isn't affected by our seasonal temperature changes, we're able to ride through and see some performance increase on the rest of our system as well. We'll have just a few more seconds. All right, so this is completed. So my system completed its analysis of the Earth's surface potentials, and we'll go ahead and plot the safe areas. And you'll note that calculation took a little bit longer because we now have 7 soil layers that we're evaluating our grounding system's performance in. And see, as expected, we do have some improvement in the central location of the substation. It's not sufficient enough to make the rest of the substation compliant, but using this approach, we could start to see improvements throughout the rest of the substation if we apply ground rods throughout. So in conclusion, I want to hit home that seasonal variation affects the soil resistivity and therefore in turn changes our grounding system performance. This is especially true and significant for systems that experience freezing down to the grounding system's depth. And in those regions in particular, we're going to see conditions that are unsafe that occur just seasonally. So even if you've done the testing in the summer, you may not have realized that in the winter your soil resistivity increases and your grounding system performance is no longer safe. And using the tools such as seasonal analysis from XGSLab, engineers can actually design a system that's going to be compliant regardless of the season. So appreciate your time today, and I'll be taking questions after this. But if you have any questions you think of later or just want to talk about grounding systems or analysis, feel free to reach me at this link or send an email or give me a call. Thanks. Bye.